This is lesson 10.8, polygons and tessellations. Prairie Pools designs and builds swimming pools in various shapes and sizes. The shapes of 5 swimming pool styles are shown in their catalog. In the pool catalog, the Aquarius and the Roman styles are listed under Group A. The Aquarius and the Roman. The remaining 3 pools are listed under Group B. Describe one difference between the shapes of the pools in the 2 groups. Well, if you look carefully, the Aquarius and the Roman in Group A have sides that are all straight. They're line segments, in other words. The Group B, the kidney, the oval, and the rustic all have curved sides, which means they are not polygons. In step 2, it says create your own drawing of the shapes of a pool that would fit into Group A. That would be this one right here. This is actually a hexagon. This would be Group B. It looks somewhat like a rectangle, but you'll notice that the corners are curved, which means this is not a polygon. It would be in the B group. A polygon is a simple closed figure formed by 3 or more straight line segments. Straight line segments. A simple figure does not have lines that cross each other. If you've drawn a closed figure when your pencil ends up where it starts, you've drawn a closed figure when your pencil ends up where it started. Some examples of polygons. Line segments are called sides. Sides meet only at their endpoints. Points of intersection are called vertices. These are all polygons. This is a triangle. This appears to be a pentagon. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This would be a dodecagon, a 12-sided polygon. These are not polygons, even though this appears to be straight sides. They cross in the middle, so that disqualifies this from being a polygon. These are sides that are straight, or line segments, but it's not a closed figure. It doesn't have an inside and an outside. This is obviously a circle. It has curved sides, therefore not a polygon. Polygon can be classified by the number of sides it has. For example, a 5-sided polygon is a pentagon, a 6-sided polygon is a hexagon, 7-sided polygon is a heptagon, 8-sided polygon is an octagon, a nonagon is a 9-sided polygon, and a 10-sided polygon is a decagon. And you'll notice that in these particular models, none of these are what we would call a regular polygon. Because a regular polygon has all sides congruent and all angles congruent. Some examples here are this equilateral triangle and this square. These little marks right here indicate that the sides are congruent. These little arcs here indicate that the angles are congruent. Now I would disagree with the way they did this one. I would make all of these 2 because they are in fact congruent to each other. If you have 1 on one side and 2 on the other, that would indicate to me that they're not congruent, so I disagree slightly with how they mark that. Classifying polygons. Determine whether each figure is a polygon. If it is, classify the polygon and state whether it is regular. If it is not a polygon, explain why. Well, in our first example, if you look at the sides, they are straight sides. It is a closed figure. It has an inside and an outside, and the sides don't cross. You can see by the little marks that all the sides are congruent and all the angles are congruent. So this would be actually a regular hexagon. Hexagon, because it has 6 sides. This, because of this curved side here, is not a polygon. Check your progress. Determine whether each figure is a polygon. If it is, classify it and state whether it is regular. If it's not a polygon, explain why. Well, in example A, the sides are straight line segments, but you can see that it is not a closed figure. It doesn't have an inside and an outside, so it is not a polygon. In example B, we have 2 sides of this figure that are congruent. This is 1, 2, 3, 4, 5. This is a 5-sided polygon, so it is a pentagon. This is often a little confusing for students because they think all pentagons look like this one, like the Pentagon building. This is in fact also a pentagon, but it again is a regular pentagon where all sides are congruent and all angles are congruent. A polygon does not have to be a regular polygon. The sum of the measures of the angles of a triangle is 180 degrees. We learned that earlier in the chapter. You can use this relationship to find the measures of the angles of regular polygons. Actually, it's any polygon, not just a regular polygon. Find the measure of each angle of a regular pentagon. Well, if we start at this vertex right here, we can draw two diagonals. That means they connect vertices that are not consecutive. That divides us into three triangles because triangles are 180 degrees. 3 times 180 means the sum of the angles is 540 degrees. Because this is a regular polygon, we can divide that 540 by 5 and find that each of the angles is a 108-degree angle. Find the measure of an angle in each polygon. A regular octagon would look like this. So I would start at this vertex and I would draw 1, 2, 3, 4, 5 diagonals, which gives me 1, 2, 3, 4, 5, 6 triangles. So 6 times 180 is 600, plus 480 is 1080. That's the measure of my angles. If I divide 1080 by 6, I get 180 degrees. Actually, that's not correct because I'm dividing by 6. I should be dividing by 8. Obviously not correct because that's a straight angle. So 1080 divided by 8 would be 135 degrees. This is an equilateral triangle. The sum of the angles in any triangle is 180 divided by 3. That would make each of those angles 60 degrees. A repetitive pattern of polygons that fit together with no overlap or holes is called a tessellation. The surface of these bricks is an example of a tessellation of squares. The sum of the measures of the angles where the vertices meet in a tessellation, like right here or right here in the diagram, will always equal 360 degrees. These squares each have 90-degree angles in all 4 corners. So 90 times 4 is 360. Ms. Evans wants to design a floor tile using pentagons. Can Ms. Evans make a tessellation using pentagons? Well, if it's a regular pentagon, again, remember the sum of the angles is 540. Divide by 5 gives us each angle is 108. If we try to divide 108 evenly into 360, it doesn't work. You can actually see from the diagram down here that you're going to have a gap. So you cannot tessellate with a regular pentagon. Can Miss Evans use tiles that are equilateral triangles to cover the floor? Well, here's an example of our equilateral triangle. Remember, in an equilateral triangle, all sides are congruent, all angles are congruent, so each of my angles is 60 degrees. And you can see from my example that I can indeed tessellate with an equilateral triangle because 60 times 6 is 360. Determine whether each figure is a polygon. If it is, classify the polygon and state whether it is regular. If it is not a polygon, explain why. Well, this is a polygon because it's a simple closed figure made up of segments. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 sides, so it's a decagon. This is not a polygon because this side, these two sides, do not meet at a vertex, so it is not a polygon. This appears to be a regular hexagon, so it is a polygon. It doesn't show that the angles are congruent, but if the sides are congruent, then the angles opposite them have to be congruent as well. So this is a regular hexagon. Find the measure of an angle in each polygon. If the polygon is regular, round to the nearest tenth of a degree if necessary. In a hexagon, the measure of an angle in each polygon. If the polygon is regular. Okay, so a hexagon. Actually, what we've done is we've developed a formula over the years. Our book doesn't talk about it, but we're going to use it here. It looks like this. N minus 2 times 180 divided by n. Now, n represents the number of sides in the polygon. If it's a regular polygon, we can calculate the size of the total of the angles and then divide by n, which would be the number of sides. So if it's a regular hexagon, that would be 6 minus 4 times 180, or 6 minus 2, pardon me, minus 180, divided by 6. So 4 times 180 is 720, divided by 6. So each of the angles in a regular hexagon is a 120-degree angle. If it's a regular heptagon, that means it has 7 sides. So 7 minus 2 times 180 divided by 7. So 5 times 180 is 500 plus 400, that's 900 degrees divided by 7. We're going to get a decimal there. We've got 128.5 degrees for each of the angles in a regular heptagon, approximately 128.5 degrees. In art class, Tricia traced and then cut several regular octagons out of tissue paper. Can she use the figures to create a tessellation? In this example right here that we've done, you can see that she cannot. The size of the angles in a regular octagon, we figured that before in an earlier example. We decided that they were 135 degrees. If we go back here and try and divide 135 into 360, it does not work. We cannot tessellate a surface with a regular octagon. Here is the vocabulary for this lesson. 1, 2, 3, 4, 5, 6, 7, 8, 9 terms should be in the student's notable and should be working on memorizing that for the test, the vocabulary test, which will be 20 points. At this point, you should quit watching the video, go to NICU, www.nicu.net, and log in and take the Lesson 10-8 quiz.